Well, good morning all. Nice to see you all. Nice to have seen you all during the so-called holiday when we're on Google Meet with you all. I hope you can you all hear me okay? Thumbs up. You can hear me okay?
Yes.
Okay. Today we're going on the whole grand tour of waves, light, sound, the photoelectric effect, everything to do with waves, longitudinal, transverse, woo, big subject. And we've invited the grade 10s and 11s, if some of them going to join us, there's because the topic affects everybody. Okay, so let's just start off. I think you can see my board. You can see the wave there. Let's get a few of the terms before we start talking about waves. Here we've got a crest of a wave. Here we've got the trough of a wave. Between there and there, or between there and there, or between there and there. That is what we call a wavelength. That's the length of one crest and one trough. And then we've got the height of the wave from the middle, and that is called the amplitude. Okay, so those are some of the terms that we use in waves. Now, what is the most important thing about a wave? Well, a wave, we used to play in a swimming pool and we used to make waves. And the way we had a nice little round swimming pool, and we would sit on a tube in the middle of this round pool, and we jump up and down, up and down. And then as we were sitting like here in the tube, we pushed up and down, and then we created these waves. And then if we could get the right frequency going, we could get the waves to bounce up and then come back to us like a swing. And then as the wave got to us, we'd bounce again, and we could actually get the water to splosh out of the sides of the pool. So the first thing we have to know is that a wave has got a source of energy. In the case of a pool, that would be us little kids sitting on our tube, bouncing up and down. And then the wave moves away. It moves at a constant speed. And we talk about the velocity of a wave. A wave has got a certain speed. Now, if you make two waves, like you bounce up and down, you bounce up and down, you get two waves, but they both move at the same velocity. So you've got to have some sort of medium, like water, that can carry your energy away from you. And this is the whole point of waves. Waves carry energy away from the source, and they just keep on carrying the energy. And some waves, some media are very efficient, and they will carry the wave endlessly. It's like if you drop a stone in a pond or a lake that is totally still. That ripple will just go out and out and out. So this, the first thing we must do and notice is, say we're bouncing up and down here, it's creating energy, and we could get somebody else who's sitting on a tube. There's somebody else sitting on a tube. We could get them to bounce up and down on the other side. So, key concept, waves carry energy. Okay, now, there's two things that affect the energy of the wave. The first is the height of the wave. We call that the amplitude. If I bounce you up and down, up and down, up and down, and I can get you to bounce nice and high, obviously I've put a lot of energy into pushing that wave up and down to get the person on the tube there far away from me to bounce up and down as well. Okay, the second thing that affects the energy of the wave is how fast I bounce up and down. So let's suppose I want this person to bounce a lot faster. I could much more quickly bounce up and down. So here's me still on my tube, bouncing up and down. And we call that, we've changed the frequency that I bounce up and down. So this frequency of the source will affect the frequency of the observer or listener or whatever is detecting the wave at the other side. So if I bounce up and down faster, my friend here on his tube will also bounce up and down faster. So there, that introduces us to the concept of frequency. Frequency is the number of times I bounce up and down, normally measured in seconds. Okay. Now there's another concept, and that is this formula here, that velocity is frequency times wavelength. Now let's think about it like this. Let's measure. Let's say that this is one wavelength. And here is a second wavelength. And here is a third wavelength. Okay, so let's say we stand here with a stopwatch and we see that 3 of those go past per second. And let's suppose each of those is 1 meter long. Okay, so imagine it's like railway trucks. You got 3 railway trucks going past, each is 1 meter long, and 3 of them go past in a, let's say, in a second. Now we can work out the velocity of the wave. Why? If 3 went past and they all are 1 meter in 1 second, we know that this wave is moving at 3 meters per second. Think about it. Or let's suppose we have a long train and it's got 100 trucks, each 10 meters long, and those pass in a minute. And we want to know how fast the train is going. 100 trucks, each 10 meters long, and they pass in a minute. Well, we know that the length of the 100 trucks would be 100 times 10 is 1,000. And that would be 1,000 meters of truck is passing in 1 minute. And then we would get the velocity of the train, which is 1,000 meters per minute. Okay, so you've got to be aware of that formula. Velocity equals frequency times wavelength. Then there's another concept, that is, how long does it take each truck or each wave to come past me? Now, if we said that 3 of those pass in a second, then how long does it take for 1 of them to pass in a second? Well, it should be obvious. It takes 1/3 of the time. So it's 1/3 of a second. And that is what we talk about as the period. And that would be 1/3 of a second. Okay. So there's another concept in waves we've got to know. The length of time it takes for 1 complete wave to pass a point per second. And then there's a relationship between that and frequency. Period equals 1 upon frequency, and frequency equals 1 upon period. You must think about it. Okay, but just take my word for it. That frequency is 1 upon period, period is 1 upon frequency. So if you know the frequency, you know the period. If you know the period, you know the frequency. Okay, so those are main formulae that we're going to be involved with in just the basics of waves. So, there were many great and wonderful people who've always wondered what light is. what does light consist of? And around about the 1600s, a Dutch scientist called Huygens speculated that light is a wave. Now, why would, I just want to swap to you guys, why would anyone start to think that light is a wave? I mean, what properties do waves have that light has in common? But you know, in the old days, they didn't have TV, they didn't have computers, they had nothing better to do than to sit and think. So these guys would sit and think, I wonder what light consists of. And all they had to around them was like water. So they would play with water and they would play with light, and then they would see, how is water similar to light? Okay, so let me just show you some of the things that water and light have got in common. Okay. So here's something that we find in a lab. It's called a slinky spring. I hope you can see it. And you see that looks like water turned on its side. And this is the first thing we notice with that we're creating a little wave. Okay, that would be a complete wave. But one part of a wave is called a pulse. Now, the first thing I want you to notice is like this. A pulse is reflected. And we can also see that light gets reflected. And so the first sort of similarity that I guess these great thinkers thought about is, both waves and light seem to get reflected. Okay, so there's our slinky. Then the other thing that we find in physics labs is a thing called a ripple tank. So this is a nice little simulator. It's on falstat.com. It's simulating water waves going outwards. Okay. So let me just show you if we've got two sources of waves. Okay, do you see there's two sources? Now, here's the first thing that I want you to notice. Do you see these radial lines? They are something we find that when two waves cross each other, they can wipe each other out. We say that they can interfere. And here they can build up. Here they interfere and cancel each other out, so you don't see a wave. And this is the first thing that began to make Huygens and other people think that light might be a wave, is because light has got the ability to cancel other light out. So we call this constructive and destructive interference. Here, there's destructive interference. Here, there's constructive interference of the two sources, meaning the wave here is twice as big as just one wave. Here, there's no waves, it's calm. And here, it's got big, twice the size crests and twice the size troughs. Now, it might be of interest to you to note that at sea, many ships go down every year from unknown reasons. And the reason is if you get a whole lot of sources of waves, and they all just happen to have their crests meet at the exact right spot, and the ship happens to be at that exact spot, you get a tidal wave, and that tsunami will knock the ship over, and the ship will just disappear, and then the wave is gone. It just appears for a short period of time, knocks the ship over, and it's gone. And that is due to constructive interference. So I just want to show you. Okay, so there's where you get no waves. Here you get double the size crests. Let's just see if I can find something else. Another property of light is refraction. Now, just watch. Here we have a straight rod pushing, straight rod's pushing out. And look, when it hits this barrier, which is shallower water, some water gets reflected, but some gets bent or refracted. And that is a property of waves. Look, these are water waves, a straight water wave coming. Some bounces off. That's a property of light. If you shine a light on a window, some of the light reflects off the window and into your eyes. That's this here. But some of the light goes through the window, but it goes through the window slightly bent, and that is refraction. So I guess these guys could see, hey, light seems to get bent and water can get bent. So therefore, both seem to experience refraction. I just want to see, there's something here. I just want to see if I can find. Okay, let me just go back to this Google Meet. And just want to stop presenting. Okay. So Huygens in the 1600s postulated that light was a wave. But there was a guy, a scientist, a British scientist called Thomas Young, who proved that light was a wave. Now, this guy took courage, because Newton said that light consists of particles. But Thomas Young had the audacity to say that Newton was wrong, and everybody thought Newton was the Einstein of his day, and Newton couldn't be wrong. So it was like this great man of science, but who said that light is not a wave. Newton didn't think that light was a wave. He wrote a whole very convincing book called Optica or something. And Newton was one of the first people to find out that if you take white light and you bend it or refract it through a prism, it splits into violet, indigo, blue, green, yellow, orange, and red. So in other words, you find that he was the first to find out that white light produced a rainbow. But I guess he had some way of explaining it by means of particles. He thought that light consisted of little corpuscles, and these little particles somehow got bent differently. We normally think of the bending or refraction of light something like this. Okay. We think of light as if you take two little wheels and an axle. And this is for the people who, like, you do this a lot in grade 11. And this little axle comes here and it hits a denser optical medium, right? That's the thing that carries the light for you. This wheel hits here and this turns. This wheel at the bottom hits the glass and it turns the whole ray slightly clockwise, and now the ray goes from being there to being bent. Now when this axle comes out again, it gets bent again, and then it produces the whole spectrum. So each wavelength is bent differently, but I don't know how Newton explained that. But anyway, let's go back to the proof. The guy who definitively proved that light is a wave. This is what he did. Here's his experiment, Thomas Young. Okay, so this is what Thomas Young did. He took the sun and he made a little slit. So here comes your wave, your light wave, and it hits the little slit. Now, what happens is Huygens had found that if you hit the slit serves as a source of a new wave. That's called Huygens' principle. And then what Huygens did was he took another piece of glass or whatever with two little slits in it. And now each little slit started to produce its own wave. And what he found was you got those constructive and destructive interference patterns that we just looked at just now on water. So he used a double slit, and we call this not refraction, but diffraction. And what diffraction produces are little areas where the waves meet and build up into light spots, and where the crests and troughs of the light produce dark spots. So these would be the dark, and these in between would be, like you saw with the ripples, the light spots. And then when you put a screen here, what you see are dark and light spots. Now, I know that you're totally overwhelmed. If I know you're totally excited about this experiment. If you put it on a screen, this is what you look at. You see light and dark spots on a screen. That's all you see. And that proves that light is a wave. Aren't you excited? Well, we did this. We used to do these kind of experiments, I remember, at Wits University about 100 years ago when I was there. I remember being totally underwhelmed by this. We would take the light, we do this exact experiments, copy what Thomas Young did. Yay! We got light and dark little spots. And we called them nodes or whatever, light nodes. And that proves that light's a wave. Hooray! It doesn't sound exciting, guys, but this is all what led to the current knowledge that we have today, that light is a wave. And then came Einstein, and he said, no, light is a particle called a photon. And so now we got a whole new branch of science. Let me just see. Okay, there's what an electromagnetic wave looks like. We can show the plane of the electric component, and we can show just. So there is what light consists of. It consists of a magnetic field. You see it runs like, how can we say, horizontally. Switch that off. And then it's got the magnetic field creates an electric field. So nowadays we know that light is a wave. There you see both fields together. The magnetic field generates an electric field. The electric field generates a magnetic field. And each of these little arrows, I can't tell what color, but they're dark and light arrows. Each little one, I just hope that you guys can see this. Am I presenting? No. Okay, so you're not able to see that. Sorry. So each of these upright electric fields generates a horizontal magnetic field. I just want to see which one's the magnetic field. Okay, the magnetic field is the one that lies flat, and the electric field is, yeah, the electric field is the one that goes up. And these two fields work at right angles to each other, and each one creates the other. Now, can you imagine how hard it must have been to figure all this stuff out? And this all travels at the speed of light, that these electric and magnetic fields are interacting and producing a change in nothing. I mean, this is all not traveling through water. This is traveling through nothing, the space. I hope you're blown away as I am. Let's see if you're blown away. Now, I'll tell you why it blows me away. I can really understand why water carries energy. I can understand that. But how can nothing carry energy? And nothing is just the space. It's just space must have a certain springiness, because everything has to be springy in order to carry energy. This must push on this, must push on the next thing. So space has got an inbuilt springiness, and the electric field generates a magnetic field, and the magnetic field generates an electric field. And you've come across this before, that when we move a magnet inside a coil, it creates electric field. And if we pass electricity through a coil, it creates a magnetic field. So electricity can create a magnet, and a magnet can create electricity, and electricity can create a magnet. And think about it. These waves can go for thousands of years, millions of years. They say the Earth, they say the universe is 13.75 billion years old. From the Big Bang, or the light from the Big Bang has been traveling through time and space for, they say, 13.75 billion years. If you want to think 6,000 years, think that. But it's lost none of its energy as it goes through space. So you see that waves, like electromagnetic waves, carry not only energy, but they also carry information. Do you know that you can see the universe as it was 13 billion years ago? You can see little baby universes that are starting to form. Why? Because those baby universes gave off light. The light contained energy, but it also contained information. We know that light contains information because you're seeing the information. That's me moving my head like this. There's my energies, my head, but the light is carrying it to my computer camera, and then it's being transmitted via electromagnetic radiation to the school, or down cables. And then it's been projected onto a screen. So waves carry not only energy, they also carry information. So when people say, hey, it'd be lovely if we invent a time machine, the answer is we already have a time machine. We can look through a big fat telescope. That's a time machine. And we can see planets, stars and planets being formed up to 13 billion years ago, or 13 billion light years ago. And you know what? If you had a big enough telescope, we can, at the moment, we can see stars 13 billion years ago. If we had a big enough telescope, we could see planets. And if we could see the planets, we could see, oh, look, there's something living on that planet. We just need a bigger telescope to pick up that very faint light that's on the planet. So maybe it would be possible. But let me tell you a secret. There is no life except here on Earth. And you want to know why? Sorry, I just did something stupid. I was dusting off my key. I hope you guys can still see me.
Yes.
I did something stupid to the screen by wiping some dust off my off my keyboard. Okay, there we're back. But I want to tell you that there is no life out there in the universe. Do you know how we know that? Okay, I know that you're going to be skeptical. Do you know that we are sending out information from Earth, all our satellite rays, light rays, we're sending all that out into space. So if there was somebody out there in space, they would be picking up our radio signals and our TV signals and all that. And you know what? If there were other people out there in space, we would be picking up their signals, but we're not. Therefore, we can say with certainty, because we haven't picked up any signals from any star, any place in the universe, and we've got nice big telescopes, we've got Meerkat, and we got square kilometer array and all that, not a single sign of electromagnetic radiation that looks intelligent. It's all stuff that comes from stars, but it's not intelligent stuff like SABC3, you know, that would be what we would call, or DSTV, something that looks like it came from some living organism. So now we know for sure that there is no life out there, and they sent an explorer to Mars. And if there's life on Mars, it's because it got knocked off off Earth. Okay, so I just want to show you a few more things, and then we'll get on to doing. Okay, I just want to show you a few more things. Okay, here again is your ripple tank. Watch what happens if we change the frequency. Here's blue light. What happens if we make it red light? Do you see how the wavelength gets longer? Now, because the universe is expanding, light that left a star and was blue gets red shifted. It first becomes yellow or green. And now watch as it travels further and further through space. It gets redder and redder. The wavelength, look at the distance between the crests, gets longer and longer. And we say that the universe is red shifted. Okay, we say it's red shifted. All the light from the most distant galaxies has their wavelength stretched from blue to red. But I want you to notice, red and blue, they all travel at the same speed, and that is called the speed of light. You cannot change the speed of light. That's the fastest that anything in the universe can travel. But we can shift it as it travels through time and space, 13 billion years. Space is expanding, and it stretches the blue light into slightly red light. So most of the light from the more distant galaxies is red shifted. Light that comes from our closer galaxies, if it was blue when it left, it's blue now. If it was yellow when it left, it's yellow now. Okay, that's what I wanted to show there. Now, just have a look at this. This is what we call a longitudinal wave. Do you see a pulse moving across the screen like that? Now, instead of it moving up and down at right angles, it's moving in the same direction as the source. So you push it this way, then you pull it, and each particle, look at that long particle gets pushed and pulled, but we can see a disturbance traveling. And this is how sound waves, they push on the air molecules, and the air molecules get compressed there and rarefied or stretched apart in other places. Stretched, compressed, stretched, compressed. And those stretches and compressions are what enables us to hear. I would say that air is a very poor conductor compared to like electromagnetic waves, because sound fades very quickly. But this is one of the things that we know that sound is a wave, because waves can like Huygens said, go around corners. We saw in our ripple tank. You see how sound and waves can go around corners. I'm just looking for somewhere where we can set up a barrier is there a barrier here, and we can show that it can go through corner? Okay, here's a double slit. Okay, there's a double slit. Yeah, you see that waves can go around corners. And there's two slits at the top there. And the waves are... So if you speak in one room, it can go around the corners and get to another room. Now, Einstein said if light was a wave, then it would be able to get around corners. But we know light can't go around corners. So there's another reason why it was hard for Newton to think that light was waves, because waves can go around corners. Okay, now we come to what concerns the grade 12s. That is something called the photoelectric effect. So when light, here's light, we can choose the frequency of light. I've got ultraviolet C. Okay, that'll give you a real suntan. Hits a metal. Let's see what metal we've got here. Let's put rubidium. Okay, so there's rubidium. The ultraviolet C knocks these electrons off the metal. The metal goes onto another plate here, and it closes the circuit. So here we're getting a circuit, and we're getting a current of 47.83 nanoamps. Okay, so here's the circuit. Light. Now let's change the intensity of light. We could go from ultraviolet, getting less and less energy. Let's go all the way to infrared. You see, infrared hasn't got enough energy. There's no current, so there's no photoelectric effect. So let's see which one. Blue? Will blue? No. Yes, blue will. Okay. Let's see if green will. No. Oh, yes, green will. You just got to wait long enough. Yellow? No. Okay, so this is the photoelectric effect. Here come photons of energy. If the light has enough energy, it'll knock the electrons off. And that electron will close the circuit, and we'll get a current. Here you see there's no current flowing. What we could also do is we could change the metal. Now, calcium requires more energy than rubidium. So calcium will require that you have a green. I don't think will work with it. You got to, will blue work with it? No, blue doesn't work with calcium metal either. Will violet work with it? Ah, there we go. Okay. So depending on your metal and depending on your light, you can get electrons. Normally this is done in a vacuum tube. Will hit the metal, knock the electrons off, and cause a current to flow. And then if you increase the intensity of the light, okay, there's 10%. You just get a few electrons knocked off. If you increase the intensity to 50%, that means you make it a stronger but the same wavelength of light. You get more electrons knocked off. And then if you have 100% of light, real bright violet light, you're going to get lots of electrons knocked off. Okay, so the intensity will determine how many electrons get knocked off. The wavelength will determine if they get knocked off. So, but the first thing is you've got to have the right wavelength. Look, this is 100% intense blue light, not a single electron getting knocked off. And this is what caused Einstein to say that light comes in little particles called quanta of energy. And these little particles must first have the right wavelength. And if they have the right wavelength, they can knock an electron off. And then, so let's give it the right wavelength. We call that the threshold frequency. And once you give the threshold frequency, the right frequency, a high enough frequency, and then you can change the intensity. But it doesn't matter what you do with the intensity if you don't have the right frequency. Okay, so that is the photoelectric effect. So let's just see just one or two other things. You can play with these other little simulations. There we can simulate. This is grade 10 work. You see that light is being reflected. The angle of incidence equals the angle of reflection. Here's your normal. Here's your mirror. You can play with these little simulations. There's lots of little simulations. But if you threw a ball could also be reflected at exactly the same angle. So reflection, waves get reflected and particles get reflected. So reflection doesn't prove whether light is a wave or a particle, because everything, both particles and light can get reflected. Let's just have a look at this. There we see our wave, amplitude, wavelength, crest, trough. We can measure a wavelength from any two points that are, we say, in phase. If you're rising on there, you'll be rising there. If you're falling here, you'd be falling there. We say those 2 points on a wave are in phase. But if you're rising, that's falling. Then you talk about it's out of phase. But any 2 points that are in phase, they're both bobbing at the same time. Those are called one wavelength apart. And I think that is about all that I've got as far as web pages. Okay. So let's just go back to what concerns you grade 12s a lot, and that is the photoelectric effect. I don't know if I've hung up, but on my side it looks like I can't see. I can see you guys. Just let's see if I've... Okay, there, we've unhung up. Okay, so let's go to the photoelectric effect, and then we're going to do some problems from paper 1 on the photoelectric effect. Where are the formulae for the photoelectric effect? E equals HF. E equals HF. And there was another formula which I just want to give you that is on your BFF or data sheet, and that is E equals work function naught plus EK. Okay, so let's just revise these formula because we're going to be using them in solving your problems. Okay. So E equals HF. This is what makes the photoelectric effect just such a nice section to do. Why? Energy of light is proportional to the frequency. H is Planck's constant, and Planck's constant is 6.63 times 10 to the 34. 6.63 times 10 to the minus 34. And that is Planck's constant. So we see that energy just depends on the frequency. You don't see any formula here for the amplitude. And that is why I think Einstein says that light is quantized, because the energy just depends on the frequency. And if you've got a high enough frequency to knock an electron on, we call that F naught. H times F naught is equal to W naught. Let's just write it here. H times F naught equals the work function. And F naught is your threshold frequency, the lowest frequency that has enough energy to knock an electron off. And then if you have enough energy to knock the electron off and you have a little bit to spare, then the rest of the energy goes into kinetic energy of the electron. So these are your two formulae, E equals HF, and then we may have work function W naught, which is an energy, equals HF naught. All of those, they're just variations of E equals HF naught or HF. So basically you've got one formula, and then any extra energy goes into kinetic energy. How nice is that? You've seen the photoelectric effect. It works on our solar panels. If you get the right metal like calcium or rubidium or whatever, you stick it in a solar panel, you stick it in the sun. The sun's got ultraviolet, it's got violet, indigo, blue, green, all the colors that Newton separated. And some of those colors you can use. Some of those colors you can't use. Like I don't think you can use red. It hasn't got a high enough, it hasn't got a threshold frequency. So whatever metal has gone into your panel, if it's got enough frequency, it will start knocking electrons off and saving you money. Okay, so let's then, I think, go. It's enough of my talking now. Let's get you guys to do a bit of work. Let's go to paper 1 and do all the questions that relate to light and waves. So I think I'm presenting. Here is our photoelectric effect. Sorry, let's just present now. Okay, and then let's have a look at our paper 1. Okay, it says the photoelectric effect. There's your energy equals work function plus any extra goes into kinetic energy and equals HF. So, presuming you're still there, just let me check. Yeah, you're still there. Yep. You're still there. And I'm presenting. Okay, let's go and work through some of those problems. Okay. Let's look for some light, waves, anything to do with waves and light. Okay, here's the first problem, 1.6. Unfortunately, it's already got an answer. We did this. The diagram below shows the electron transitions P, Q, R, and S between different energy levels in an atom. Okay, now do you know that light comes from electrons first? This is the base of the atom that's closest to the nucleus. If you heat an atom, like your filament of a bulb, the energy causes the electron to rise to a higher energy level. We say it's an excited electron. This is E naught or ground state. Then as it falls back, depending on the length that it falls, you get higher frequencies of wavelengths. So which one of the following of the transitions will result in an emission of a radiation with the longest wavelength? Remember, longest wavelength, least energy, and it's going to be R. Why? Because it falls the shortest distance, least energy in the fall. If you drop a brick that high, not much energy. You drop the brick all that way, lots of energy. That would be like ultraviolet. Let's have a look for some more wavy they're normally at the end of the paper. The spectrum of an element from a star shows some absorption lines. These lines are produced because, now this I haven't taught you. Okay, so if you've got a star and it's giving off light, and that light passes through a cloud of gas, cold gas. Some of the wavelengths of that light, as they pass through, get absorbed by that cold gas. And then you get a different color. You get different type of light emerging on the other side. This is called the absorption spectrum. The spectrum of an element from a star shows some absorption lines. These lines are produced because atoms absorb energy when moving from an excited state to a lower energy state. A cold gas absorbs certain frequencies of light passing through it. That's what looks promising. A hot gas can absorb certain frequencies. No, it's only a cold gas. Atoms release energy when moving from an excited state to a lower energy state. No, because they're talking about absorption lines. Now, absorption lines are when frequencies pass through a cold gas and absorb some of the energy and release light only of certain wavelengths. So it's going to be B. Okay, as I say, I didn't teach that to you, but just try and remember it. Okay, let's go to the next paper, and it's waves. Okay, 130. Light of a certain frequency is incident on a metal surface, and photoelectrons are emitted from the surface. If the intensity of the same light is increased, what will happen? The kinetic energy of the emitted photons increases. The kinetic energy of the emitted photons decreases. The number of photoelectrons emitted per second increases. The number of photoelectrons emitted per second decreases. Well, remember, we saw that when we went to here. We said if you increase the intensity of the light, you get more photoelectrons. So the intensity only increases the number. Okay, so there's your answer. The number of photoelectrons increases with the intensity of the light. It's like on a dull day. On a dull day, my photovoltaic panels only give me a small voltage, a small amount of electrons because the clouds and everything are in the way. Okay, let's go on, 130. A line emission spectrum is formed when an excited atom moves from now an emission spectrum is when something hot gives off energy. So it was like our first question, when you have something hot like a star or a filament, and that filament has excited electrons falling. So we're looking for excited electrons to be falling. A line emission spectrum is formed when excited atom, right? It should be electrons, moves from a higher to a lower energy level and releases energy. That sounds right. Higher to a lower energy level and absorbs energy. No. Lower to a higher energy level and releases energy. No. If you go from lower to higher, you absorb energy. Lower to higher energy level and absorb energy. Yeah, but that's not going to give you an emission spectrum. Emission means emitting light. You emit light when electrons fall from a excited state back towards the nucleus of the atom. Okay. When light of a certain wavelength is incident on a metal surface, no electrons are ejected. Which one of the following changes may result in electrons being ejected from the metal surface? Can we increase the intensity of the light and get, if there's no electrons? And again, the answer is, if we went back to this simulation, if you don't have the right wavelength in the first place, you can crank up your intensity till it's like you're staring at the sun. It's not going to make any difference if the wavelength is wrong. The thing you've got to fix is you've got to fix the wavelength, the frequency. So we must increase the intensity. No. Use light with a much shorter wavelength. That sounds right. Use metal with a larger work function. No. We need metal with a smaller work function. Will knock off electrons easier. Increase the surface area of the metal. Ha ha ha. You don't fool me with your foolishness. We've got to use light with a much shorter wavelength. Okay. So we got to get the threshold frequency. You guys must be able to associate short frequency, short wavelength, high frequency, high energy. Let's look for waves. Okay. The possible atomic transitions in an excited atom of an element are shown below. This is the fourth energy level, third energy level, second energy, first energy level, or ground state. Which transition will produce the spectral line with the longest wavelength? Remember, long wavelengths are lazy waves. They've got a very short frequency. Hang on, wait. Long wavelengths, lazy, they've got a very low frequency. Okay. So which transition will produce spectrum lines with the longest wavelength? That means laziest. Look at that. One, that's short, jump, longer jump, biggest jump. So we're looking for the one with the shortest fall. Will have the longest wavelength. And so that is going to be P. I hope you see how easy these are. I love this Doppler section, but they're not really asking us much in the way of, not Doppler section, this work function and all that stuff. In an experiment on the photoelectric effect, a scientist shines red light on a metal surface and observes the electrons are ejected from the metal surface. Later, the scientist shines blue light with the same intensity as the red light on the same metal surface. Which one of the statements below will be the correct observation as a result of the change? The number of ejected electrons per second will increase. The number of ejected will decrease. The speed of the ejected electrons will decrease. The maximum kinetic energy of the ejected electrons will increase. Okay, so think about it. And you're going to use this one. E equals a work function plus kinetic energy, EK. Okay, so that is the formula that you're going to use from it. So if you're increasing the energy, you're not changing the work function, but you are adding to the kinetic energy. The work function is the amount of energy that they will need to be ejected. So I hope you can see here that if we change the energy, we're going to, and it's got enough energy to come off, it's going to increase the kinetic energy. So I would say that the answer must be D. The maximum kinetic energy of the ejected electrons will increase. You see, because when he shines red light, electrons are ejected. Then when he shines blue light, electrons are rejected. So the only thing that's changing is your work function of the metal hasn't changed. The only thing is you've increased the energy, so you're cranking up the kinetic energy of the electrons. Okay. The wavelength of a monochromatic light source P. You know, that means a laser, something that gives off just one wavelength. You know, like you saw in Hong Kong when they used to shine those lasers in the eyes of the cops there. That's a monochromatic light when you've got a laser pointer. So the wavelength of a monochromatic light source is twice that of a monochromatic light source Q. So wavelength of P is twice that of Q. So here's Q. Q is the one with a shorter wavelength. Okay, the wavelength of monochromatic light is twice that of monochromatic light Q. The energy of a photon from P will be how much that of Q? Again, in this section, you've got E equals threshold frequency plus kinetic energy. And surely if you double the frequency, you're going to double the energy. And surely the only thing you're going to get is twice the energy. So the wavelength of monochromatic light P is twice that of monochromatic light Q. The energy of a photon of P, okay, P will be half that of Q. So that must be half the energy, because it's got, the energy is just equal to the frequency, and the frequency is related to the wavelength. You've got to be able to play around in your mind. So we've got a longer wavelength, we've got shorter frequency, or we got half the frequency, we got half the energy. So that looks like the answer. (180). In an experiment on the photoelectric effect, the frequency of the incident light is high enough to cause the removal of electrons from the surface of the metal. So now we know it has exceeded the work function. Okay, that's what we know, that the frequency is greater than the work function. Okay, the number of electrons ejected from the metal surface is proportional to the kinetic energy of the electrons, the number of incident photons, the work function of the metal, the frequency of the incident light. Okay, in an experiment on the photoelectric effect, the frequency of the incident light is high enough to cause the removal of electrons from the surface of the metal. The number of electrons ejected from the metal surface is proportional to, normally we say the number of incident photons. Yeah. In other words, if you increase the light intensity, you're increasing the number of the photons of that light. More photons are hitting. It can't be the kinetic energy of the electrons. It can't, the work function's not changing, and the frequency is not changing. So the only thing that's changing is a light of greater intensity has got more photons that are bumping. So I hope you can work that out. But the kinetic energy of every single electron is not changing. Here, the diagram below shows 4 energy levels of an atom. The transition of the atom from high energy levels to low energy levels results in the emission of a photon. Which one of the following transitions will lead to the emission of a photon with the shortest wavelength? A short wavelength means a high energy, because I hope you, I mean, please become familiar. The longer the wavelength, the lazier the wave. The shorter the wavelength, the higher the frequency. So a short wavelength is a high frequency. So we're looking for the highest frequency. Okay, the highest frequency would be E3 to E0. Let's see if there's an E3 to E0. There we go. Okay, 190. Let's carry on. Light of a certain frequency is shone onto metal M, and the electrons are ejected from the surface. The same source of light is shone onto another metal N. The electrons ejected from the surface of metal N have much higher kinetic energy than that from metal M. Okay? That should tell us that N has got a lower work function, meaning it takes less energy to eject it, and therefore more energy goes into kinetic energy. Again, we're saying that energy equals work function plus kinetic energy. Okay, so this means that metal N has the same work function as N. No. Metal N has a larger work function. No, it has a smaller work function. The threshold frequency of metal N is higher than that of metal M. No. The threshold frequency of N is lower than that of M. Yeah, N requires a lower frequency to knock the photons off. And therefore, more of the energy can go into kinetic energy. There's more leftover energy. I hope you guys can see when you, especially when you go over it, I hope you can see the logic behind it. Because I'm not asking for hands now, I'm just going through these. Okay, I've seen this question before and I hate it. I'll probably get it wrong. In an investigation on the photoelectric effect, the graph of maximum kinetic energy versus frequency was obtained for a certain metal as shown below. The intercepts P and Q respectively represent. Okay, Q looks like the threshold frequency. P looks like the work function. I would say it's C. But I don't know. This one, I remember seeing this one before, and I remember thinking, so if I had to guess, I would say that's a specific frequency. It looks like a specific frequency of this is the frequency at which the electrons start to be emitted. Below that frequency, they're not emitted. So that looks like Q looks like the threshold frequency. But now I'm just a bit worried. P is a specific type of energy, but I don't think it's Planck's constant. And I'm not happy that it's threshold frequency, because there is the energy that would correlate to the threshold frequency. As I say, I remember seeing this question before and being puzzled by it. And I saw a question similar to this. They asked, what is the slope of this graph? And the slope of the graph, I think, is Planck's constant. So I don't think it's that one. If I had to guess, I'd choose C. But I'm going to leave that one. I'll ask someone who knows more than me. I'm thinking of a teacher that I used to teach, we teach with. Yeah, here's another one that's going to be the same horrible question. The graph below, obtained from an experiment on the photoelectric effect. Which one of the following represents the gradient of the graph? Okay, we have E equals HF, which means that H equals E upon F. And 1 upon lambda is the same as frequency. So I think what they're saying is the slope of the graph is Planck's constant B. I vaguely remember that one as being the correct answer. But again, I would like to check that. So what do? The slope of a graph is vertical over horizontal. Try and find something that has got E upon 1 upon, or E upon 1 upon lambda, which I think 1 upon lambda is the same as frequency, and therefore H is equal to E upon F, because F is equal to 1 upon lambda. And then you get, that must be Planck's constant. Horrible, horrible question. Don't know why they ask it. It's because science is being captured by mathematicians, and they love doing these torturous things to us. It's a stupid question, by the way. 1.130. A learner writes the following statements about the emission spectrum of light in a notebook. An emission spectrum is formed when certain frequencies of electromagnetic radiation pass through a cold gas. No, that's what we call an absorption spectrum, when it's cold gas. So that's wrong. I just want to mentally make a note. The lines in an emission spectrum of an atom have the same frequency as the corresponding lines in the atom's absorption frequency. I don't know. The lines in an emission spectrum have the same frequency as the corresponding lines in the atom's absorption spectrum. And may be true. I don't know. So that's a possibility. An emission spectrum is formed when the atom makes transitions from a high energy to a lower energy state. Okay, so we know that's definitely correct. This may be, I might have to go and do some research on that. Let's see which of these we choose. Okay. Well, we're not left with a choice of 3 only. So it's got to be 3 and 2 because we know 1 is wrong. So 2 must be true. Okay, so there's the answer. Okay, so I've learned something. That if an atom absorbs at a certain frequency, it also emits at a certain frequency. So 2 must be correct as well. So if you say have hydrogen gas giving off certain lines, it would also absorb those lines if light passes through it. It must be true. So it must be 2 and 3 because I can only see 1 is definitely wrong. So 1 and 3 is definitely wrong. So it must be that. We're getting to the end of these. I can see. The work function of zinc is greater than that of magnesium. Okay, so it means it's harder to get electrons off zinc than magnesium. Which one of the following statements about the threshold frequencies of the metals is correct? Okay, I know that the threshold frequency of zinc must be higher. If the work function of zinc is greater, the threshold frequency of zinc is greater. And there we go. Let's just see what the distracting were. The threshold is lower. Both zinc have the same? No. The threshold of zinc and magnesium are independent of their work functions? No. So it's obviously that one. And I think that might, no, we've got one more. Consider the statements below regarding the photoelectric effect. The photoelectric effect proves that, okay, here's an important point. The photoelectric effect is supposed to prove Einstein was correct when he said light is quantized. In other words, light comes in little particles. Light has a particle nature. I think that's what it also means. But it's not supposed to prove that light has a wave nature. So where Einstein was differing was he said that light has also got a particle nature. So it's quantized and particles. So it must be 1 and 2. And there's your answer, C. But light is also a wave. And you see, this is the thing that fooled me. You know that light has got little particles called photons. But if you look it up, photons have got no mass. So to me, why call them a particle? They're just a little ball of energy. So these, to me, it sounds like you're splitting hairs to say that light has a particle nature, because it's got little balls of energy that are quantized. They have definite amounts of energy. My question is, where do these photons fit into the wave? Because if a light has got a wave function and a photon function, do waves consist of little balls like this, all joined together like a necklace of beads? I don't know. Where do the photons fit in this wave theory? And you know what? I'm not Einstein. I don't know. Presumably, he could figure it all out. I haven't devoted enough time to figuring it out. But anyway, all you've got to know for matric is light is quantized. It has particles, namely photons. Those photons have got zero mass, so why call them a particle? Just call them a ball of energy. And that's what we say. If something's got a specific amount of energy, it's quantized. It's got a quantity of energy. Okay, so there we're done with those. Let's see what our time is doing. Okay, guys, how are you? I feel like I've just been talking to myself here. Tell me, do you guys think that when you go through these questions, you will be able to get them right now? If you think you will, won't you just put up a hand? If you think you going through those questions, you would get them right now. Okay, put up a hand if you think you'll get them wrong now. Okay, at the back there, if you think you're going to get them wrong, what are you going to do? You're going to go and read through them. And if you've got any questions, I'll bet you even, I think I know who's at the back there, who's got the hand up. Okay, so at the back there, can you now tell me why you would get them wrong? What part of that would be difficult? I need someone to come up and shout that a bit clearer to me. You're going to be my mouthpiece. Okay, who's going to come up and be who's going to just say the question a bit louder? Okay, there we got someone coming up. Thank you. Okay, what is it that you would struggle with there? What is it? I can't hear you. Okay, just tell me, what is it that you would struggle with in this section? Hey. Okay, Jade. What would you struggle with? I don't know if you can hear me. Oh, you guys can't hear me. Just let me go back to here. Can you hear me now? Because your microphone is working. Okay. The best I can suggest we do is just go through paper one. Okay, it seems like we've lost everyone. So I'm going to end now. Okay, cheers, Matsadiso. and Vincenzo, I hope you learned something, but I think we've lost them, and I'm going to just end now.